So thanks for the invitation to speak. It's a great honor to be here and to speak to all of you. So today I'm going to talk to you about a certain type of topological faces that are called, well, first of all, I'm going to talk to you about fractons. These are special type of faces, and then I'm going to talk to you about Planon-only fracton orders. So as others have said, I'm going to be talking about something that many of you in the audience know better than me. Some certain places my knowledge feels like this. That's better?
Yeah, that's okay. That's not your fault.
Not me, but my mic wasn't on, so maybe. But I think, okay, yeah, so my mic's on. Hopefully this sounds better. Yeah. Yeah, so, and that's, you know, there's definitely many places where my knowledge is a bit shallow. So if there's a question and I don't know the answer and somebody in the audience knows, I mean, I don't mind if somebody steps in and answers. So I just wanted to let you know that. Okay, so this is going to be joint work with my collaborators. So first there's Michael Hermley from the University of Colorado Boulder. He's a professor in physics. And it's because of Dan Fried that I know him and that I have this collaboration. So thanks, Dan. And then there's Wilbur Shirley, who's a postdoc at the Kanoff Center for Theoretical Physics at the University of Chicago. Evan Wickenden is a graduate student of the University of University of Colorado Boulder, working under the supervision of Mike. And at the end, I'm going to mention most of the work is going to be about a paper that I wrote with these guys. But at the end, I'm going to mention some like future directions and ongoing work that also includes Bowen Yang, who's here. Okay, so let's see. Today, I'm not talking about TQFTs. I'm entirely going to be talking about lattice models, okay? And I'm just going to sort of set the stage for it. So we have a lattice, and I'm going to put my spins. I'm going to put them on the edges. And so we get a Hilbert space by tensoring all the spins together. Of course, I'm going to be thinking about infinite lattice. And of course, I need the C-star algebraic language to make that precise. But I don't want to worry. We don't need to worry about that level of precisions here. I'm just going to sort of say, OK, so all of the Hamiltonians that I write are always going to be written down in a way that you can kind of think of it loosely as just some tensor product of spins. So they're going to be, so what are going to be my interactions? So I'm going to have local interactions, which are going to be interactions supported on a finite number of lattice sites, okay? And the sum of all the local interactions is going to be the Hamiltonian, which is going to be modeling the energy of the system. So these are going to be finite range interactions. So we're going to put a bound on the diameter of how far apart spins can interact. And the energy spectrum is going to be sort of the energies of E, and we're going to have a ground state. So on an infinite lattice, I'm going to be looking at systems that have a unique ground state, okay? And that ground state is going to be called the vacuum, and it's going to be the state that minimizes the energy of this Hamiltonian. And the excited states are going to be the ones that have higher energy than the ground state. And we're going to impose a gap, as usual. So there's a positive distance between the lowest energy and the energy of any of the excited states. OK, so this is familiar to people. And so the prototypical or canonical example is Kitaev's Toric code, which I know you spent some time on last week. I'm still going to go, the Toric code is going to be my way to sort of tell you how I'm thinking about the things I'm going to generalize and the algebraic models I'm going to write down. So I'm going to still spend some time sort of putting us all on the same page about the Toric code, okay? So we're going to put qubits on each of the lattice sites. So we're going to qubits on the edges, and we're going to have a Hamiltonian, which is going to be a sum of two kinds of terms. There's going to be plaquette terms and star terms. So the plaquettes are going to be X operators for each two cells. So one X operator on each of the edge that borders that two cell. And the star operators are going to be, a Z operator on each edge that borders that vertex. Okay. And of course, when I mean like a bullet Z or just an operator on an edge, I mean just tensor it up with all the identities on all the other sites. Okay. And the ground state, so this, on an infinite lattice, this has a unique ground state, which minimizes all of the terms of the Hamiltonian, okay? So in Milan, it's all the plaquettes and all the star terms. Okay, great. So that's like, sorry, I didn't realize my slide was going to go back, but that's the prototypical example, and we're going to come back to it and talk more about it for me to set up the language that I want to have us to have in common. Okay, so of course, we all know about stacking. So you have two systems, you put one on top of the other, tensors the Hilbert spaces, and the Hamiltonian that you get is this Hamiltonian over here. And the trivial systems are going to be the decoupled systems. So there's just no interactions. Huh. Either Ezra was having a thought or he likes decoupled systems.
It's not gapped. Yes. It is gapped.
Yeah. So I just mean you can have a term, you have one term, so there's no terms that mixes.
It's non-zero. Oh, yeah. There is a look. Okay,
yeah.
sorry.
Okay, so now the reason I'm doing this slide, although everyone knows what it is I want to sort of point out the two steps that gives us the phases. Here I put Gauto, Johnson, Fried, like in the spirit of where we learned it. That Konstantin said in his talk. So, okay, so there's two moves for phases. So the first is we can stack with a decoupled system. So decoupled systems are like a free resource. And if we do that, then we think of, we sort of can integrate out the decoupled system and think of this as being Q. So this is like stabilization. That's how I think of this. The other one is if I have a system and I can deform it in the space of allowable Hamiltonian, whatever that means. So without closing the gap, then I get a new system, then I'm going to think of these as being the same. Okay, and this is the concept of deformation. Okay, so hopefully we're all used to this. And I think of this process, I think of this as homotopy, and I think of this as like a kind of group completion type of things. All right, great. So now here's a property that we like about phases. It's a certain scale independent. So a phase should be scale independent, and it should be like a fixed points for the action of the renormalization group. So let me give you an example of what that means. Imagine you have a lattice, and the lattice constant is L. So that's like the distance between the lattice points. Okay. And imagine I put a toric code on that lattice. And there's a way to deform it. So by applying local unitaries, you can sort of implement this as a homotopy. So you can implement this as a deformation. And you'll get a toric code on a lattice, which has twice the lattice constant, but is also stacked with a bunch of decoupled layers, okay? But now we said we can integrate out or cancel the decoupled layers by this other move, which is stabilization, and then we get a toric code on a lattice with twice the lattice constant, okay? So now the phases of the toric codes does not depend on the lattice constant, so it's independent of lattice coarsening, and so it's invariant under like, my collaborator put it, it's invariant under squinting, okay? All right. So this is something which we'll see is more tricky with Fracton phases. That's why I'm bringing this up. Okay, so now we're gonna spend some time with the toric code. I know you all know the toric code, but I decided, not knowing how to pitch this talk, I decided to pitch it to myself a year ago. I knew some things about the toric code, but it wasn't at the tip of my fingers, so that's the person I'm pitching the talk to, and I'm sorry if that's not you. Okay, so let's talk about the state. So we have the vacuum, and for the vacuum, I'm just like gonna draw it as a gray lattice. None of the terms in the Hamiltonian are excited, okay? But now I have other excitations. So there's certain kinds of excitations where they have the property that they excite exactly one of the term in the Hamiltonian. So this would be an excitation for the star operator, BV, and it sort of, so that would be the only term in the Hamiltonian that's excited. All of the other terms remain in their lowest energy state, okay? And I can create this excitation by acting on my infinite lattice torus code by an infinite string operator like so a bunch of X operators, okay? And that's gonna excite that, but nothing else. Okay, so that's one kind of excitation. I have a similar notion for the plaquettes. So these are like the generating excitations. So if I have, I can excite exactly one of the plaquettes by applying this infinite string operator. Okay. Okay, so now fusion. So the excitation turns out to form a group, which is the fusion group. Okay, so how do I do it? I can create M and I create E, and then I get a composite excitation, which is the composite of the two. And in the Toric code, we usually call that one F. Okay. And now the fact that, so for the Toric code, it doesn't matter in which order you do this. So this is the fact that the Toric code is a model of is a theory of abelian anyons, and the word abelian means that the fusion group is abelian, okay? And I'm only gonna think about theories of abelian anyons. So that's the kind of thing you wanna keep in mind. Okay, and now the mobility, so that's really important for the Fracton. The reason I'm going over this is that in fractons, these will be different. So how do I implement mobility? Well, I act by local operators. So if I act, here's a local operator, just like these two x terms. If I act on the system like this, I can move my star terms. So from the v vertex to the v prime vertex. Okay, so by acting by local operators, I think of that as moving the particle, the excitations around. I can do the same for m. Okay. And I'm going to think of mobility as being implemented by local operators. Okay, so if you want to move an excitation, you have to do it by applying a local operator. And in this example, all the excitations are fully mobile. You can imagine that I can move them. I can move all the e particles to any e particle to any other e particle and any m particle to any other m particle. Okay. So now that brings us to the idea of like these these local operators play a role, an important role. So what does it mean for an excitation to be locally creatable? Well, it means that I can act by a local operator, and that creates the excitation. Okay, sorry, I went one slide ahead, but so in here, so over here, I've acted by a local operator and I created this composite excitation. Okay, so that composite is locally creatable, and same, I can create this one, but some creation operators are not local operators, okay? So for example, that was not a creation, that was not a local operator, so M is not created by a local operator and neither is E, okay? All right, so now this brings us to the concept of superselection sectors. So the fusion group, modulo the locally creatable excitation, that's gonna be the group, that's gonna be the group of superselection sectors, and from now on, I'm always going to denote that group by S, okay? All right, so for example, in the group of superselection sectors, these two are equivalent because they differ by a local operator, and therefore there's one equivalence class of E excitations. In this one, these two, again, differ by a local operator. So again, there's one equivalence class of M excitations. And it turns out that S is generated by E and M. Okay, so there's one more non-locally creatable excitation. It's the composite, the F excitation. And the E here, this one is not locally creatable, as we saw. However, think of this. So suppose that so this is what created E. Suppose that I want to sort of add E to itself, right? It's a group and I want to understand the group structure. So I can create another E, and that's the stack of, that's the fusion of these two. So then I get something that's obtained from my vacuum by applying this infinite string operator, but this doesn't excite anything. So that's the vacuum, and therefore E squared is 1, and the fusion group is 2 torsion. Okay. All right, so the fusion group is 2 torsion, and I want to think of it this way. Okay, so what happened? I had my E and M. So just think E and M is the equivalence class here, but just think of picking like a representative, E for one vertex and M for one plaquette, okay? And the system is translation invariant, so all of the other excitations in the fusion group I can obtain by applying a translation operator, okay? So Tx is for one direction, Ty is for the other direction, and I can get all of my E excitation labeled by some polynomial times, you know, in T plus or minus 1 and some polynomial, so Laurent polynomial in T y plus or minus 1 times the generators that I picked. However, the action of local operators imposes relations, okay? And I get relations like this. We saw that if I move one way, I can implement moving an E particle one step by a local operator, so that's trivial. So I get the following relations, and then you get that the fusion module is Zima 2 squared, okay? All right, so this kind of expression is what I'm gonna sort of generalize in the next kind of models. Okay, and then I have one more topic to talk about the Toric code, and then we'll move on. So now there's there's more to the Toric code than just a Zima 2 squared group. There's also statistics from it, and the first kind of thing that we can sort of extract from this model in terms of in that theme is the braiding. So suppose I have an E and M particle. Imagine taking the E particle on a walk around M by applying this loop operator. Okay, so this is just I just move E around M. Well, as I do this, I had to cross a creation operator for M. I put it here, but no matter where I put it, I have to cross it. So it turns out there's a well-defined phase. Okay, so just take the vacuum, pick a vector in the vacuum, and look at the phase of, you know, the difference between this is a commutator, the difference between first walking, applying the loop operator and the creation operator and vice versa. And if you think about it, right here something happened, right? I had to commute these, okay? And therefore I pick a -1 phase. Okay. So, and you can compute that this is the braiding for the Toric code. Okay, so now there's another, so this braiding actually, there's actually a quadratic form that implements the braiding, right? So if I have a quadratic form, I could get a symmetric bilinear form. And that quadratic form is a little trickier to think about. You have to do like, it's the idea, it's kind of like you want to do this, you want to do a half braid, but to really get what you want, you have to do the half braid in a kind of funny way, okay? So the way you want to do it is you need to move like this, okay? All right, so that gives you an operation that you can do, and for any excitation, all the X operators commute on all the plaquettes, so I don't get any statistics. But if I do this composite excitation, if you follow through, something happened right here, you ended up having to commute these two, and so you get that there's statistics for the F operator. Okay, and that's the quadratic form. Okay, so now if I can define then a 2D theory of abelian anyons, so this is going to be a pair consisting of a finite abelian group. So for a 2D theory, it's going to be a finite abelian group and a quadratic form. And this is what I'm going to think, well, I will call, this is not me, like this is like Kitaev and Kapustin. You know, there's going to be lots of names in the bottom of the slide, but we're going to call this an algebraic theory of 2D abelian anyons. So now there's a principle, which is the principle of remote detectability. It's that any excitation is detected by an operator supported very far away from the excitation. So this is sort of the picture that I have in mind. And mathematically, this corresponds to the non-degeneracy of the braiding. Okay, so physical systems should have that property, and therefore the braiding should be non-degenerate. And so it turns out that for 2D theories of abelian anyons, this is sufficient for physical realization. So any finite abelian group and non-degenerate quadratic form arises as fusion and exchange of the superselection sectors of a 2D lattice model. Yeah.
That the F is completely determined by the braiding? If so, do you have a specific form for it?
I'm sorry, I know you're talking about like the F symbol in the MTC, and I don't remember which one it is. Yeah, so I don't know the answer to your question. Again, the audience is welcome to chime in.
Yes.
Yes, okay, perfect. Okay, thanks. Okay, so now stacking corresponds to the sum of the quadratic spaces. So what's a quadratic space? It's just a pair like this, okay? And this leads to width and Gerthlini width invariance for these phases. So this is like the width groups of like finite abelian groups and quadratic forms. These appeared in the previous talk. And so don't worry if you, I'm gonna talk a little bit more about this equivalence later, but this equivalence, this is the equivalence that's imposed when you're passing to width groups. And this corresponds to a physical process called condensation. And I will say exactly as much as I know about what condensation means on a few slides down. So that one I'll be super shallow on. Okay, so now the algebraic theory becomes a powerful tool for studying these systems. Okay, so now this is really nice, and we'd like to always have these kinds of models when we're studying lattice models. Okay. So then what about higher dimension? So let me check. So here comes Fracton models. So I decided to just use a quote because it sounds nice. Okay, so this is a quote from Nankishore and Hermele in 2019, and this is for one of their papers on Fracton orders, and it says that Fracton phases are characterized by excitations that exhibit restricted mobility, being either immobile under local Hamiltonian dynamics or mobile only in certain directions. Okay, so now this is why I went through the whole Toric code and the mobility, right? So Fracton models are not going to have this kind of full mobility that the excitations for the Toric code had. Okay, so the sort of one of the canonical example of a Fracton model, although it's not the first one, is the X cube model. Okay, so I think the first Fracton model comes from Chamon, the Chamon model. Okay. And now we're going to have four types of term. Okay, so we're going to be on a 3D lattice. Again, I'm going to put my sights on my edges, and then we're going to have cube terms. Hopefully, it's clear from my picture now that we went through the Toric code, or maybe before. Like that means I'm just putting an X operator on each edge that borders the cube, and then I'm going to have three kinds of star terms. Okay, and so. Now, for the X cube model, let's think about the excitations. So the excitations for the cubes are just going to be, there's going to be one for each cell, okay? And they can be created using these half-plane creation operators. There's three times of star excitation, one for each sort of orientation of your star, okay? And again, they're created by infinite string operators, okay? So these are not locally creatable excitations. Okay, so now there's also this one, but this one is redundant. It's a composite of the other two, if you think about it. Okay, so really I'm just gonna mostly, in my next slide, talk about the X and Y star excitations. All right, so now I've got so let me try to remember what's happening here. Right, okay, mobility. Let's look at the kind of mobility that we have in this X cube model. Okay, so I can act by a local operator here, and it's going to excite these three and cancel out the bottom edge corner. Okay, so now if you pick local operators and you're trying to move a generating cube excitation, you're always going to create other things. Okay, so you cannot move it. The cost of moving it is creating other excitations. Okay, and for this reason, this is what we call a fracton. So this is an excitation with no mobility. Okay, so it's very different from the E particles and the M particle. That one doesn't want to move. Okay, so now we also have the star excitation. So I can apply this local operator and I will move it over there. That's fine. However, if I try to move it vertically, I'm going to actually create a star excitation for the other orientation. So I can't move it vertically. I can move it horizontally, but not vertically. And so these are called line-ons. Okay, so these are excitations with mobility restricted to a line. Okay. So now the Planon-ons, so my cube was not, I couldn't move it. But if I take this composite excitation of two, so I can fuse two cube excitations, this one I can move up. And if you think about it, I can move it in the plane that's also perpendicular. So I can move it in the YZ plane. Okay. So that's why it's called the Planon. It's got mobility in a plane. Okay, so now let's think about the superselection sectors. So the X cube model is going to have there's like two parts to the superselection sector, the X sector and the Z sector. So the X sector is the one generated by the cube excitations. Okay, so again, this is a translation invariant model. So I can just pick a generator and I can use a Laurent polynomial ring in 3 variables to sort of move it around and sort of capture like the generating excitations. Okay, so I'm going to start with that. I just pick a generator and I think of a Laurent polynomial. So I want to, this is also the fusion is also order 2, but I'm not going to go over that again. Okay, but then these the action of local operators is going to impose some relations. We already saw one, right? When I went from 1 to 3, okay? These are the relation that we get, and that's the X sector, okay? And the Z sector has a similar sort of presentation. Okay. So now don't worry about like parsing out, did I get these right? Do you understand every single one of these? Whatever. Doesn't matter. Like I just want to show you like I have this Laurent polynomial ring and generators and local operators impose relation, and then I get my super selection sectors is actually a module over the Laurent polynomial ring on 3 generators. How do we want, I didn't write this down, but let me say it. How do I want to think of this? This is the translation group, right? This is the translation invariant. This is right, this, whatever. I'll just say the translation group, this is Z cubed, right? So it's a module over the group ring of the translation group. Okay. So now here are some problems. So can we develop an algebraic theory of abelian fracton orders that characterizes the universal properties of excitations above the ground state? Okay, so this is a problem that's subject of ongoing research. Okay, so there's lots of open questions here. Okay. Now, there are examples of work that go a long way towards there. There's Ha's algebraic theory of commuting polycodes. Like this was pretty groundbreaking setup for understanding commuting polycodes. And there's follow-up work in terms of understanding the invariants from Ruba and Yang's homological invariants of polycodes paper. Okay, so these are examples of work in this direction. So in January 2025, my collaborators, this was before I joined them on this project, they put up a paper called Planon, a paper that defined a concept of Planon modular fracton orders, okay? So a Planon modular fracton order is going to be characterized by the property that any non-trivial excitation is going to be detected by braiding with a planon, okay? So let's think about planons for a second, right? I have my planon, and that has that excitation is fully mobile in a plane, right? So that means I can move it around. So I can sort of try to define braiding by thinking I'm going to try to move that around other, excitations and see what I get. Okay, so you just do a creation operator, you apply a loop operator for it, and you see, okay, do I pick up any phase or anything like that? And you can sort of think of exchange as well in this context. And it turns out that this setup includes examples like Chamon's mode, the X cube model that we saw, the 4-color cube model. Okay, so these are different lattice. These are examples of fracton orders. So these are the examples that people study and test their theories against. Okay, so but there's things that it does not understand. I don't think it includes Ha's cubic code, but okay, don't quote me on that. All right, so now let's go back to the slide. Remember the slide about the scale independence of the Toric code? Okay. Well, this is very different for fracton model. So imagine I put an XQ model on a lattice of like lattice length L. Okay, I didn't draw it because it got complicated. And then it turns out I can deform it, so I can apply some local unitaries and turn it into an X cube model where the lattice length is 2L, but then I'm going to be stacked. So remember, with the Toric code, we stack with decoupled layers. Now, what I'm going to pick up is stacks of Toric codes, okay? So it's going to be like layers of Toric codes, okay, in various directions. Okay, so now I wanted to integrate out or cancel the decoupled systems, when I was doing stabilizations, but these are not like the stacks of 2D Toric codes, these are not a trivial phase, okay? So therefore, you can't sort of perform that last step, and this has been like sort of a pain in trying to understand fracton phases, that this sort of idea that phases should be scale independent sort of seems to fail. Okay, so I think there's a lot of recent work on like reinterpreting how we think about scale independence and whatnot that sort of addresses this problem. But up until maybe last year, this was sort of the state of affairs. Okay. Okay, so then that leads to a different notion. So this is the notion of foliated fracton phases. So in a foliated fracton phase, you can integrate out 2D layers that can be non-trivial phases to impose invariants under the action of the renormalization group. Okay, so maybe like we had a 3D system and maybe you're feeling, okay, integrating out 2D Toric codes, not so bad. Okay, whatever, I can get used to this. But the issue is that for other Fracton models, the things you pick up are like kind of the same, like have the similar properties as the X-cube model. So that's like where the unhappiness with these kinds of things came, okay? If it's just 2D layers of Toric codes, we already understood the 2D theories, so maybe we're okay with that, okay? And one thing that's great about these Planon-only Fracton orders, which I'm not going to talk a ton about Planon-only. Sorry, the thing that's great about Planon modular Fracton orders is that, so if you do this process, so I quoted them because I mean, I just decided to say it the way they say it. But the thing that happens is that if you're looking at that special class of Fracton orders that they were looking at, which includes the XQ model, when you do this, the only thing that you're going to pick up that you're going to wish to integrate out are going to be Planon-only Fracton orders. Okay, I haven't told you what those are yet. Okay, so I was pretty glib about Planon modulo Fracton orders. It's like that class that they studied, okay? But the point is that the stuff you're gonna end up wanting to integrate out is gonna be another class of Fracton orders, which are much simpler to study, and that's gonna be the subject of the rest of my talk. It's gonna be these Planon-only Fracton orders, okay? Yeah.
Seems the Haas model will not belong to this class.
Yeah, exactly. That's the one. You have like the B. Yeah, okay. Yeah. That's the one I was like saying sometimes it's just like it's even worse. Yeah. Oh yeah. Okay, so I can hear myself. What should I do so that I don't, okay, I think it stopped. Okay. All right. Okay, so now let's talk about what are these, yeah.
The X has a line on, so do you allow Planon and Planon?
In Planon modulo Fracton orders, you do allow Linons and Planons. The thing is that with Planon modular Fracton orders, the importance is that you can detect anyone with braiding with a Planon. Okay, that's like other kinds of particles with restricted mobilities are allowed, okay?
You even have fractons.
There's a subtlety that I just not remember off the top of my head, like of what's allowed and what's not. But let's say like a priori, yes. Let's, okay. I wasn't on that paper, right? So I like, yeah, so there's a subtlety about, there's some restriction, but I think you can definitely have, I think you can have line on. I'm not sure if because of the properties, I don't remember, I think maybe you can have like fully immobile particles, okay? So there's something, but I'd have to look in the paper to answer your question confidently, okay? All right, any other questions? So great, okay. All right, so now I'm gonna restrict. I'm gonna restrict to Planon-only Fracton orders. Let me say these are an example of Planon modular theories, like from their previous paper, but now this is an even simpler class, okay? So we just like reduce the problem until you can solve it and then work back up, right? That's how life works. Okay, so what's a Planon-only Fracton order? This is gonna be a 3D gap quantum phase with translation symmetry Z cubed, okay, in which all excitations are abelian particles fully mobile in planes with a common normal direction, okay? All right, so let me explain that. So I'm gonna call the generator for the common normal direction Z plus or minus 1. This is a group isomorphic to Z. Okay, so I've got my plane of mobility. So there's a plane, there's a fixed sort of normal direction, and there's a plane. And in that plane, so the particles are fully mobile in that plane on which they live on. And it's translation invariant, so I can sort of propagate the particle using Z, using T, just like we did. We just apply translation symmetry. Okay. So then that sort of leads to a very sort of simple algebraic description for the fusion modules. So what is going to be the fusion module for these things? So what should be like our axioms for it? It should be Z, a module S over this Laurent polynomial ring, okay? and it should be finitely generated. And this is just the idea that a finite number of excitation types can fit into a finite spatial volume, okay? The next thing that we're going to impose is, so this is, you don't have to impose this, but this is in our study. So I'm only going to look at finite order Planon-only Fracton orders, where order is used differently in those two terms. So I'm going to ask that all planons have a finite order n, and so I can think of S as a Z mod n module over this ring, where the coefficients are Z mod n. Okay, it's nice to think of it globally for stacking. Okay, so if you remove these conditions, there are interesting examples that I don't know of. So I read the intro to my paper, and that's what my collaborators tell me, and I haven't thought of, but we don't treat those. Okay. And we ask that it be torsion-free. Okay, so I'm going to explain what I mean by that. So by torsion-free here, I mean torsion-free with respect to, I mean, obviously there's torsion, right? I just asked them to all be torsion. But now suppose I fix the sort of minimal n that achieves that where all the planons have that order, then I can think of S as a module over this. And now I can define what it means for S to be torsion-free over this ring. And that just means that if RA is 0 for A and S and R in there, where R is a regular element, so R is not a zero divisor, then A had to be 0. Okay, so it's just the same as torsion-free, except you just test with non-zero divisors. You don't want to test with zero divisors. And okay, so why is that the same thing as no fully mobile particle? Well, you can show that if you have an excitation, A, and a regular element such that RA is 0, then you can find a K such that T to the Ka is equal to A in your module, okay? So although A might not be like mobile like this, eventually it can jump a bunch of planes. So if I just coarsen my like notion of translation symmetry, suddenly I get a fully mobile particle because it's already mobile in a plane, and then it becomes mobile this way. It's fully mobile. I'm out of the realm of fate or systems that I decided I would study, okay? So this is what this assumption is doing. Okay, so my little picture for the statistics. So now we have, sorry. So let me just go back, and I think if I hold a button, Okay, so this here, this is going to be the algebraic model for fusion of a Planon order, Fracton order. Okay, so that's it. That's the kind of objects we're going to study. And then the next thing is, okay, let's study the statistics of this thing.
In this picture, the R is actually T.
T, there is there an R? They're all T's.
My eyes is
Yeah, so T cubed, T squared, P, yeah.
Okay. I didn't see.
Yeah, I know, I'm using red. It's like not really nice to everyone. Sorry. Okay, so let's see. Okay, questions about that before I move on? All right, so now I want to define the statistic, and the idea is that I can they're all planons, right? So they all have a full plane of mobility, so I can sort of move my particles around like that, and I can use it. I can do the same thing as I did with the Toric code, and I can see if I sort of braid two things if I pick up any non-trivial phase. And so we get an algebraic model for braiding. Okay, so I'm going to call a P theory. That's going to be just the model for braiding. Okay, so a P theory is going to be just a pair where S is as before. Okay, so S is an allowed fusion module for a Planon order, Fracton order, a Planon-only Fracton order. I'm going to have a symmetric bilinear form. Okay, instead of, these are all finite. So instead of using U1, I'm just using Q mod Z. Okay, so it's like, if you want to do U1, go e to the 2 pi I. Okay. So this is going to be a symmetric bilinear form, and it's going to satisfy the following properties. So my little video here, so maybe I should have, okay. So suppose that I have my two excitations. One is on like this plane, this one's on that plane. Nearby, there's like noise and stuff, okay? But if I move it far away using my translation, eventually they're not gonna talk to each other anymore. And so this is a kind of locality for the braiding. Okay, so the braiding should only really care about things. Sorry, let me just say it mathematically. So it's exactly the little video that I showed you here. If I move y very, very far away from x, then I'm gonna braid trivially. The next one is going to be translation invariance. So that one, I just move my picture around. It's not going to change the braiding. I'm going to ask for non-degeneracy. So this is just implementing the principle of remote detectability, because why? I know that it's necessary for 2D abelian 2D theories of abelian anyons for physical realizability. And as we'll see in a couple of slides, what's an example of a Planon-only Fracton order? You just take a 2D theory and you just repeat it infinitely in two directions. So you expect that the braiding should not be degenerate. Yeah.
Is that like a base module? Is there a distinguished basis for it, or is it just a module? It's just a module.
Yeah. Okay. So then the algebraic model for exchange, well, it's going to be, okay, so we just kind of think of it similarly. So it's going to be a quadratic form, and then we ask that the associated bilinear form, which now I've written additively because I'm using Q mod Z, is local and non-degenerate. Okay. And then so a pair where I have one of my S's and one of my thetas, this is going to be a Planon-only theory of excitations. Okay. So that's something that you would expect from something that you can realize physically. And now the question is, are all Planon-only theories of excitations physically realizable? Okay, so we've asked the same conditions as in 2D theories, and we hope that that was enough. And the answer is just no, they're not. Okay, so let's look at an example. So first, before I look at the example, I need to tell you the concept that's going to let us look at the example. So this is the idea of compactification. So I can compactify fusion by imposing an n-step translation invariant. So I'm going to take the module and I'm going to mod out by t to the n minus 1, okay? And the result is going to be some finite abelian group, okay, like this. So now it's just a zero-dimensional system, a 2D system, so one dimension lower. And we obtain a candidate for a 2D theory, which is the quotient and the induced form that you get on it. Okay. So for a physically realizable theory, you would expect that for n large enough, the theta is non-degenerate, because there's a locality to the statistics. And if you go n large enough, the statistics, it should just look locally like a 2D theory, okay? And the problem is there are theories of excitations as I've defined them. So a non-torsion-free, finitely generated S fusion module where the compactifications are degenerate for all n, okay? So let's see an example. So let's take Z mod 2, adjoint. So we're going to take, I'm going to make the fusion module just be, so I'm going to make fusion be order 2, and I'm going to do a rank 1, a free rank 1 module over the Laurent polynomial ring, okay? And I'm going to, my generator I can call P, but let's just, I pick a generator, but let's write PI for T to the I P, okay? So it's just the translate. So now I just have like a stack of, so I just have layers, and I have one excitation per layer. And I'm going to define the braiding to be the following. So I can, if I braid with somebody right above or right below me, then I pick up a half. So so if you're thinking of U1, it's like -1, okay? And you braid trivially otherwise, including with yourself, okay? And you can check that you get this is realized by the following quadratic form. And this is not, this is a non-degenerate form on this module. Okay, great. However, let's look at the compactifications. So for any n, this is the compactified module. I just get a finite abelian group generated by P 0 up to Pn minus 1. I forgot to change this to Z mod 2 for the mathematicians. I'm going to define the following excitation. So this is the composite excitation. I just take the sum of all the generators. And then I try to braid this, okay? And I get 0. Okay, so for any x, I get 0. So this compactified form is degenerate for all n, okay? And the reason, to see this, just check on a PI. You just pick a generator, and it's 0 on all the generators, so therefore it's 0 on everyone. Okay, so this theory is not, its compactifications are not physical, so the principle of remote detectability for Planon-only Fracton orders is not sufficient for physical realization. Okay, and let's see how we could have seen this before the compactifications. So I'm going to define a detector to be a string operator of planons that may have infinite spatial support in the direction transverse to the plane of mobility. Okay, so a detector is some sort of infinite string operator. So this is a loose definition. So we don't have like a working definition for everybody, but I can be precise of what I need the detectors to be for this class of Fracton orders. In general, it's a loose definition. There's not really a real definition yet. But here's an example of what I would mean. So I just take the sum of all the PIs, okay? Just like the infinite by infinite sum. That is not an element in my module because the sum of all the TIs, that's not in a Laurent polynomial. That's a by infinite power series, okay? So now bilinearity and locality of B allows us to extend the braiding to the detectors, okay? I should have put a tilde on my next slide. There's gonna be a tilde on the extended braiding, but I can define the braiding by just sort of using bilinearity to pretend like I know what to do. And then now I know that this form is local, so X can only braid non-trivially with a finite number of the PJs, so I get 0. And so the detector, this thing is not effective. It doesn't detect any non-trivial excitations. So it kills all the generators, right? So it's gonna, again, kill everybody, okay? So there's no X that my detector detects. Okay. So then that leads us to the definition. So roughly, detectors are operators with support where the support lies at spatial infinity. So detectors for Planon-only Fracton orders, we can be specific about what we need the detectors to be. So we're gonna write, okay, I'm gonna write Z double brackets T plus or minus 1. This is not Laurent power series. It's like by infinite series. It's the Z linear dual of Z adjoint T plus or minus 1, okay? It's gonna be the collection of series with no restriction on the coefficients. They just have to be, integers. And the module of detector of S is going to be the tensor product of my finitely generated module with this guy. Okay? And then again, the braiding extends because of the locality to a braiding on the detector. So I can braid I can't braid 2 detectors, but I can braid an excitation with a detector. And we're going to say that a detector is effective if it detects at least one non-trivial excitation. That is, there's an X such that this is not 0. And okay, so what we prove in the paper is that if you have as theta a theory of excitations, the following are equivalent. The extended braiding, so the braiding with detectors is both left and right degenerate. And the compactified theories are modular theories of 2D abelian magnets for all n greater or equal to 0. So asking that B theta be non-degenerate is equivalent to asking that the compactified theories are physical for all n. Okay, and now this brings us to, well, okay, the principle of remote detectability was not enough, so we're going to upgrade it. So this principle subsumes the principle of remote detectability. So this is going to be the excitation-detector principle, and it says that every excitation is detected by some detector, and every detector is effective. And this is the left and the right non-degeneracy of B tilde. Okay, so now I just repeated what the excitation detector principle is here, okay? And we're going to call the theory of excitations perfect if it satisfies the excitation detector principle. And the conjecture for the realizability conjecture for Planon-only Fracton orders is that all perfect Planon-only theories of excitations are physically realizable. So this is a conjecture with like a sketch that we it's a conjecture because we haven't sort of worked out the program yet, but so Evan has explained to me like how he thinks this can all be done using these. Okay, so polynomialized Chern-Simons theories type things. Okay, so here we're in a realm that I don't really understand, but like there's a plan for realizing it, so I think they know how to do it, provided that the details work. All right, so now, the summary for algebraic theories. So, and by the way, if that plan executes, if it doesn't execute, it'll be fun. There'll be more math to do. And we're missing something. But if that plan executes, that means that this excitation detector principle is necessary and sufficient for physical realizability. So by physical realizability, I mean like you can find a lattice model that sort of realizes it. Okay, so the summary for algebraic theories of Planon-only Fracton orders then is, okay, so I'm just going to put them up. I just want to sort of wrap together all the things we did. I'm not going to say them again. Okay, so I just sort of put the properties that I talked about on the first few slides on that side. Again, you can stack these. It's just, take the direct sums of the modules and the stack of the sum of the quadratic forms. Okay, so in the time that's left, I want to talk about, okay, right, sorry, I have to talk about decoupled layers. Let's go back to the foliated phases, okay? So a theory of excitation is going to be called decoupled layers if it's equivalent to an infinite stack of 2D theories of abelian anyons. Okay, so I have a 2D theory of abelian anyons. Now I'm going to call the finite abelian group A and theta the quadratic form, and then I just copy it, okay? And this is the same as just inducing the form, okay? And so something that we show is that a Planon-only theory of excitation with fusion order a prime is always decoupled layers. So if your fusion order is a prime, then there's just nothing interesting that beyond the 2D theory that happens. And this comes from generalizing a version of the dominant diagonal theorem for Laurent polynomial rings. If you know about the classification of forms on abelian groups, you'll know what I meant. If not, don't worry. So that means that the classifications reduces in that case to 2D abelian anyons. And it brings us to a notion of foliated phases where we're going to write S is equivalent to S prime if they differ by decoupled layers. Okay, so this is sort of going to be the free resource is going to be these decoupled theories. And this is a pre-theorem. I'm not going to state it. So it's pre because, I mean, we haven't all sat down together and done it all together. So, but it's even written. The proof is even written up, but has not been proof checked. Is that we have a classifications for foliate phases where the order is p squared. I mean, it's a classification up to indeterminacy. It's not as satisfying as what we wanted, but there's something. We have a lot to say about that. Okay, so now. Right. So now we have this notion that comes from like the theory of quadratic forms of a symmetric space, okay? So a finite order symmetric space over this Laurent polynomial ring is going to be a finitely generated module together with an isomorphism from S to the dual. And I realized that I wanted to have torsion here, okay? Otherwise, this would be the wrong dual, but okay. So I should have added torsion, okay? So in this context, so if I look at these kinds of symmetric spaces, then a perfect P theory, so that's a P theory, that's an S and a P, that's like where the thing is perfect, that's actually equivalent as a symmetric space, okay? So the non-degeneracy of this B tilde, if you're willing to think sort of more in module theoretic terms and think about thinking about the form, you can redefine the form to have values in a Laurent polynomial ring, and then you can start thinking about the form as like just a map to the dual. If you rephrase it that way, that's the same as that map to the dual being an isomorphism. Okay, so we're really just looking at symmetric space in a certain context. And the context fits into the theory of exact categories with duality in the sense of Schlichting. Okay, so Schlichting has a setup, so we have it fits into the machines that people do to sort of compute L theory with theory and whatnot. In fact, I think it also fits into the theory, they're into Poincare infinity categories, and there's a candidate for what it is, but I'm going to let Roman talk about that on Friday because he's studying a slightly different problem, but we are coming to the same, but where the same sort of L theory is sort of popping up. So because of this setup, we can, there's going to be notions of width classification and Grothendieck width classifications. And here, okay, so here we need to make a definition. So if I have a subset, a submodule of S, the orthogonal complement is going to be all the things that braid trivially with X, okay? So I just think of my braiding, right? So this is this isomorphism. You can think of the braiding from before. So I just think of I fix X and I take, I take I look at the Ys that are gonna break trivially with everything in L, okay? And L, a subset of S, is going to be a totally isotropic subspace. So that's going to be the definition. If L is contained in its complement, so everything in L breaks trivially with itself. And we're going to also ask that the quotient is torsion-free. So in the language of exact categories, this is that the inclusion is admissible. Okay. And so there's an interpretation in terms of physics of what this means, okay? So suppose that I have a totally isotropic subspace, then the interpretation is that there should be a gap interface between S and this quotient with the induced form, okay? So, and this is like the notion of condensation. And this equivalence, this is the equivalence you impose when you're doing width groups. Okay, to make S equivalent to that for totally isotropic subspace. I mean, it's not usually how it's defined, but you can check like that's really what, that's one thing, that's one way you could think about it, is to always impose that equivalence. And again, pre-theorem, because not, it's written in some notes, but it's not like double check and triple check and discussed, is that up to condensation, any P theory of fusion order P to the K is decoupled layers of prime fusion order. I just haven't thought through the order when you don't. So the way we study these things is like one prime at a time. We just localize. So we've thought a lot about order P to the K, and I haven't thought about if this, sort of how this glues. And, if essentially we can give an explicit proof of this in this context, but this should just come from also the abstract theory of like the fundamental theorems for Laurent polynomials and Grothendieck width classifications. So there's probably like a, the 9 author papers on like doing quadratic, Poincare infinity categories, blah, blah, blah. There's number 4 coming up. And apparently number 4 is going to contain all the computations we could dream of for this kinds of setups. I look forward to it. Okay, and mathematically, this is just saying that the width group for this exact category with duality is just the same as the Z-mod P width group. I'd like to point out that this is not, if you know what this is not a split exact category. So there's something more than to it than you would get in that context. So work in progress and future work. So of course, we'd like invariants and classifications. So we'd like to classify foliated phases for all fusion order and find some computable invariants, okay? We have some stuff in progress on that. And it'd be nice to have framework and generalization. This is like a toy example, this Planon-only Fracton orders. It'd be nice to understand P-modular Fracton orders and other Fracton orders. And this is the part that's joint with Bowen. So we have a sort of, we've done a lot of work towards defining the braiding and the statistics for other Fracton orders using these kinds of ideas. And sort of the algebraic model that we want would come from, probably the best place to put it would be in this context of Poincare infinity categories, although you can probably phrase it I don't know, let me not say what I was going to say. Let me just stop my sentence there. Okay, and this is related to work that of Ha on classification of Clipper QZAs, and generalizations by others. In particular, Roman's going to talk about this on Friday. Okay, and then I'm a homotopy theorist. So I'm interested in the high homotopy groups. So what's like, we're saying Grothendieck width groups, L groups. There's a these are pi naught of spectra. The higher homotopy groups should have meaning. Like one obvious thing to think about is about quantum pumps. But we're seeing all these things about what are they called? Categorical spectra, right? So that's sort of, I'm going to go home and have some things to think about on that direction. I think that's pretty cool stuff. So thank you.